Dear students, from the previous lecture, we started looking at the actual DRAM based main memory and its memory controller. In process, we looked at the physical DRAM organization. A quick recap of that: we have multiple channels, and each of those channels can have multiple DIMMs, dual inline memory modules. Each DIMM is specified by its CAS ACT pre-latencies. Here 11, 11, 11 are the number of cycles, specifically the DRAM cycles it would take for each of these commands. Along with this information, the DIMM will also be specified by its data bus frequency. Here, for example, it's 1600 megahertz. Each DIMM we realized that is made up of DRAM devices or DRAM chips. Each of these chips can be imagined as if it's a mini DRAM, because whatever happens in one DRAM device happens across all the other DRAM devices. And a DRAM device is specified by its width, x4, x8, so on. Basically, the width gives us an insight on how many layers of DRAM arrays are stacked in the third dimension. DRAM devices, when grouped, form ranks, and the number of DRAM devices that would form a rank would be given by the channel width on top of the device width. Ranks are divided into banks. Banks are further divided into rows and columns. This is where we have left in the last lecture. Let's continue. Let's assume this is one DIMM. It has 4 DRAM devices of x16 width. Now when we say that the channel width of this DIMM is 64 bits, now the number of DRAM devices that would form my rank is given by 64 on top of 16, which is 4. It means that these 4 devices work together to give me the 64 bit of data. Each of these devices gives me 16 bit. So when we send a command to the DIMM and a rank, here these 4 devices form the rank, all the 4 devices respond to it. And when we send a cache, each of them will supply 16 bits and we get 64 bits per cycle to the memory controller. Now when we say that each DRAM device or my rank is having 8 banks, it means that each of these devices has 8 similar portions which are called sub-banks. There will be some peripheral circuitry across the x-axis of the chip. Typically, it would be the column decode logic, column mux, and the global bitline drivers. And on the y-axis, each of these sub-banks will have its own row decoders, global level, and global word line decoders. And some common area is there in the chip which has the control logic and all the IO drivers, which eventually drive the 16 bits of data from the sub bank to the periphery of the DIMM. Like I mentioned, all the DRAM devices look similar. So all the DRAM devices here are having 8 partitions. And when the memory controller identifies one bank, it means that a portion or a sub bank in each of these devices is identified. And when we say that the physical page size is 8 kilobyte at the rank level, it means that each sub bank contributes 4 kilobyte. So when we send an activate to this DIMM, the activate goes to each of these 4 devices to that specific to that specific subbank and opens 2 kilobyte page in each of them. Together, the memory controller sees that there is a page of 8 kilobyte. So with that, let's look at some questions for practice. How do we calculate the number of DRAM chips per rank? We have just seen that we would need both the channel width and the device width, and the number of DRAM devices or chips is given by channel width upon device width. Now, how do we calculate the number of ranks a DIMM has? For this, we would need the total DIMM capacity, the DRAM device capacity with which this DIMM is made of, and the DRAM device width along with the channel width. Let's look at a small example. Let's consider a 16 GB DIMM consisting of X8 devices, each of which has a capacity of 4 gigabit. If the channel width is 64, let's try to calculate the number of ranks in this DIMM. To start with, we are going to find the number of DRAM devices in this DIMM. We would get that by dividing the total DIMM capacity with the capacity of each DIMM. Here it's 32 DRAM devices. Now, because it's an X8 device, we need 8 such devices to form a rank, and we have 32 such devices. It means this DIMM is made up of 32 upon 8, 4 ranks, or the other way to put it, this DIMM has 32 DRAM devices which are having a width of 8. So this DIMM is actually made up of 4 ranks. Now with this, along with this, let's try to calculate the peak bandwidth of the memory. For this, we would need the data bus frequency along with the channel width. Now let's say the frequency on the DIMM is given as 1200 megahertz for the address bus, and the channel width is 64 bit. It means that in each cycle, at 1200 megahertz, we would get 264 bits of data. Why? Because the data bus works at twice the frequency of the address bus. So the bandwidth is 2 times the address bus frequency times the width of the channel. Here it is 19.2 gigabytes per second, Gbps. A quick overall picture. If we say that the total memory size is 32 GB, it will be, for example, split into 2 channels. There can be 1 DIMM per channel, and each DIMM can be made up of 4 ranks, and each rank can be made up of 8 banks. Each bank is made up of 64K rows, and each row can be made up of 128 columns, and the standard column size is 64 bytes. Now if we reverse calculate, 64 byte times 128 times 64K times 8 times 4 ranks times 2 gives us the overall main memory capacity. Now with this understanding, let's look at the DRAM address mapping. When a request comes to the memory controller, mainly because it's a mess from the caches, we know its physical address from the TLB or the page table. We need to split that physical address into the DRAM address. Specifically, we need to know which channel it would go to, which DIMM, rank, bank, row, column. If we are able to get this, we interpret that as a DRAM address. Now for a given physical address, how do we find out this DRAM address? Here we need what's called as DRAM address mapping. Let's look at a couple of examples. Let's assume that this is the physical address that has come to the memory controller. The column offset, which is always 6 bits because the column size, standard column size is 64 bytes, will be removed from the LSB. After that, the log to the base 2 here, ln, log of the total number of columns per row will give us the column ID. Following that, we can have the number of rows in a bank. Following that, banks per rank, ranks per DIM, number of DIMs per channel, and eventually the number of channels. So if we extract these bits, we would get 6 bits for the column offset, which we are going to neglect because we are always going to supply the 64 bytes. Always remember that memory is byte addressable. Following these 6 bits, we would get the column number, row number, bank number, rank number, DIM number, and channel number. This can look pretty standard, but we know that there is some limitation of accessing many of these components in parallel. So if you want to exploit that parallelism, we can split the address into something like this. The LSB 6 bits can be the column offset, neglected. Following that, we can have the channel number. Why is that? Because two channels can be accessed completely in parallel. It means if I want two 64-byte cache blocks, for example, if we map them to two different channels, we can get them simultaneously. Following that, we can have the column number. Why is that? We want as many columns as possible in the current request to be mapped to the same row. Following that, we can have the bank number. This is mainly because we can access two banks almost in parallel, right after one after another. Following that, we can have the rank number. Following that, we can have DIM, and at the last we can have the row number. This is one address mapping which has been explored quite extensively. In general, the memory architects consider all the target applications for which they are building this current processor and do an extensive design space exploration with many possible address mappings and pick the one which would give the most performance. That will be encoded in the actual memory controller. So this is the first task of our memory controller, the address mapping. Basically, by looking at the physical address, it needs to extract all the channel, DIM, rank, bank, row, and column numbers. Now, once we know all the details, and also we know whether it is a read or write, the memory controller will place them in either of the read queue or the write queue. These are called transaction queues. A typical entry in either of these would be the address bits, which can be the DRAM address, followed by few extra status bits. Now, there can be multiple requests waiting at the memory controller for service. Can we do anything here? We can follow or come up with a request scheduling algorithm to improve the overall performance. We already know that writes don't result in stalls at the core, so we can deprioritize writes when considering reads. It means if we have multiple reads and writes waiting in the read queue and write queue, we will try to service the request in the read queue first and then the write queue. This is the typical read over write algorithm that we saw at the caches also. In addition, within each of these read queue and write queue, we can have multiple design options. We can go for a first in first out algorithm, which is, you can say, age based, or we can go on with any other priority based scheduling. Because each request comes with some status info, we can look at the status info to make this decision. For example, if the current request is of high priority as indicated by the core, we can prioritize it so that it can go back to the core as fast as possible. So all these are part of the read queue, write queue and the request handling. This is the second job of our memory controller. We know the basic DRAM operations. A quick recap here. There is an activation operation which basically opens a row in a bank. We have a cache, column access strobe, using which we can read from the row buffer or write to the row buffer of the bank. Accordingly, we have a read cache and a write cache. We have a precharge operation which will basically close the row in the bank, and we have a refresh operation which will refresh some predefined number of rows in that bank. So these are the typical commands the memory controller can send to the actual DRAM bank. Now, unlike the pipeline and caches, these operations are very slow. In fact, each of these commands or operations can take tens of cycles, DRAM cycles themselves. So let's try to look at those timing parameters now, which forms our timing protocol. TRAS is the row access strobe delay. Basically, it is the minimum time between issuing an act command and a pre command. So only after TRAS time, after sending an act command, we can send a pre command. Another timing is TRCD, which is row to column delay. This is the minimum time it would take for us to read a row and write it into the row buffer. So the way to interpret it, this delay is, this is the minimum time between an act and a cache. Another timing constraint is tcache, column access strobe delay. This is the minimum time between the issuance of a cache command to the bank and arrival of the data from the bank. It's also called column latency, TCL. Another timing is TRP, row precharge delay, which basically is the time taken by the precharge command. Another timing constraint is TRC, which is row cycle time. Basically, it is the minimum time between issuing two activates to the same bank. Why would we do that? If we want to access two different rows in the bank, we would send an activate, probably send a cache, and then close the first row, then open the second row. So TRC is the minimum time we would need to do such a thing. TRC is TRAS plus TRP. It is the time for activation and the time for precharge. With those basic definitions, let's try to understand them cycle by cycle. Now the figure on the right side can be a sub bank or a bank, because whatever happens at the sub bank is same as the bank. So whenever the memory controller sends a command to the rank, all the sub banks of the bank identified will respond. Now let's try to understand cycle by cycle. Let's consider this as our timing diagram. We'll try to understand the working by having three different aspects, by looking at three different aspects: the address command bus, ACB, the row buffer, and the data bus. So let's try to track the working of the DRAM commands using these three. Let's assume that we have sent an activate command. If you observe, the activate command is taking one full cycle because the address bus works at the typical one cycle frequency. Sorry, one cycle of the frequency given. Now, TRCD is the minimum time it takes for the row decoder to decode, select a row in the bank or sub bank, and write it to the row buffer. At the end of TRCD cycles, the data in the row buffer will be stable. At this moment, on the address command bus, we can send a cache to this bank. After T cache time of sending a cache, we would get the data out. So we would get 8 bytes per cycle because the data bus works at twice the frequency of the address bus. In the first cycle, we get 8 bytes. Following that, in the second data bus cycle, we get another 8 bytes. Third, 8 bytes. Fourth, fifth, sixth 8 byte chunk, seventh 8 byte chunk, and the last 8th 8 byte chunk. Together, this form our 64 bytes of column. To transfer these 64 bytes, we need 8 cycles, 8 data bus cycles or 4 address bus cycles. That is given by the T burst. Apart from the timings we have seen so far, we have few other additional timing constraints. We have TRTP, which is read to precharge delay. This is the minimum time we need to wait between a read cache and a write cache. TWR is the write recovery delay. This is the minimum time we need to wait to issue a precharge after we have issued a write cache. TCCD is column to column delay. This is the minimum time we need to wait to issue two back-to-back cache commands to the bank. TRRD is row to row delay. This is the minimum time we need to wait before we can issue activates to different banks of the rank. So it means if I have issued an activate to, let's say, bank 0, I need to wait TRRD time to issue another activate to some other bank, let's say bank 7. We also have another timing, TFAW, 4 bank activation window. What this enforces is during this TFAW window, we can issue only 4 activates to the banks of a rank. Now, even though the rank can have 16 banks, we can't issue 16 activates until we meet this T4 constraint. So only 4 of them can be given at a time. The reason for having this timing constraint is the activation operation in a DRAM is very power hungry. So in order to limit the peak power consumption of the DRAM device, we have the T4 limit. We have another timing constraint, which is TWTR, write to read turnaround time. This is the minimum time we need to wait between the write cache and the read cache to the same bank or different bank of the same rank. RTRS is rank to rank switching delay. This is the minimum time between issuing any commands to any banks of two different ranks of the same DIMM. If we look at some numbers, what is the time between two activates to the same bank? Assuming that we are closing the previously opened row, the minimum time we would need is TRC. What is the time between issuing two activates to different banks of the rank? Of the same rank, it is TRRD, row to row delay, but for different ranks, we have an additional timing constraint, which is TRTRS followed by TRRD. So this way, we need to look at all the possible command combinations and come up with the minimum time of issuing the commands back to back. A few important timings that we have seen for a bank. So if we consider this as the current command in y-axis and x direction, we have the next command. The minimum, if we want to follow up and activate by another activate, it is not possible because we need to close the page first. So this is not a valid combination. If we want to follow up and activate with a read cache, we need to wait for TRCD time. If you want to follow up with a write cache, we need to wait for TRCD time. If you want to send a pre-charge to the same bank after an activate, we need to wait for TRAS time. And if you want to send a pre-charge to the bank after an activate, assuming that it is closed promptly, we need the minimum time that we need is TRC. We can't send an activate after sending a read cache. The time between two read caches is TCCD. The time between a read cache and a write cache is TCCD. And the time between a read cache and a precharge command is TRTP. Read cache and refresh, we can't follow a read cache with a refresh, so it's not applicable. We can't send an activate after a write cache. We need to wait for TWRT to send a read cache after a write cache. Two write caches need to be apart by TCCD cycles. We need to wait for TWR time to send a precharge after a write cache, and we can't send a refresh command after a write cache to the bank. After sending a precharge, we need to wait for TRP time to send a activate. We can't send a cache command after a precharge. We need to open it with an act. Same with write cache. If we have already closed the row in the bank, there is no point of sending another precharge, so it's not applicable. We need to wait for TRP time to send a refresh command to the same bank after sending a precharge command. Now, after sending a refresh, we need to wait for TRFC time to send an activate. We will shortly look at what TRFC means. We can't send a read cache after refresh. we can't send a write cache after refresh, we can't send a precharge after refresh, and we need to space out 2 refresh commands with TRFC timing. So this is the timing protocol we need to follow to access one bank. Now imagine such a protocol across banks of the same rank, across ranks of the same DIMM. So the DRAM memory controller needs to keep all these timing constraints in mind, which forms its timing protocol. That is another job of the memory controller, timing block. Following that, another job of the memory controller is page management. What do we mean by page management? Here page is the actual DRAM page, the physical page. When a request, whether it is read or write, arrives at the MC, after address mapping, we know which rank, bank, row and column it goes to. From that, we can estimate whether it would be a page hit, page miss or a page empty. In order to determine this, the MC needs to maintain information about which row is open in which bank. Now if we have, let's say, one DIMM and it has 4 ranks and each rank has 8 banks, it means now the memory controller needs to have an entry for each of those banks. Together there are 32 entries for this DIMM, and in each entry it needs to store which row is open. Based on that, it will compare the incoming request row and bank, and then it can find out whether it's a page hit, miss or empty. So all this information forms the page table. Again, this is the physical page table. Don't get confused with the page table we have discussed during the virtual memory. This page table is part of the memory controller. After identifying the request as hit, miss or empty, now it will insert appropriate DRAM commands into the next level queues, which are called command queues. Now when we know that the latest request is a page hit, all we need to do is send a cache. So a cache command is inserted into the command queue. If it is a page miss, then we insert a pre, act and cache in that order. If it were a page empty, then we need to insert an activate and a cache for this particular request into the command queue. Typically there will be one command queue per rank, but there are many modern processors which have command queues maintained per rank per bank. It's based on the performance and area trade-off. A typical entry in the command queue would be the DRAM address followed by the command act cache pre and few other status bits that can help in further scheduling. So that is the page table part in this block diagram. And the command queue. The command queue is a queue of DRAM commands for each request, and we can have multiple such command queues. Few practice questions. What is the minimum delay of memory access for a request which is page hit? It would be the T cache delay. If it is a page empty, the minimum time we need is T RCD plus T cache. If it is a page miss, then we need to send a precharge to. So it would be TRP plus T RCD plus T cache. What is the best case delay for the memory request? The best case delay is when we have a page hit. It is the T cache delay. What is the worst case delay? Here it is a page miss. So we have the delay of precharge, activation and cache in that sequence. With that, I'll pause this lecture. We'll continue more looking at the memory controller in the next class. Thank you.